Welcome to this lecture. You may kindly recall that in the earlier lecture we had discussed the analysis of variance in a multiple linear regression model. This is a test for testing the null hypothesis that all the regression coefficients are equal to 0 or not. So, through the test of analysis of variance, we are judging the overall adequacy of the model. Now, we have two options. Suppose the results from this analysis of variance, they indicate that H0 is accepted, or second option is that H0 is rejected, right. So, in case if H0 is accepted, then there is no issue. We understand that none of the variables are going to contribute in explaining the variation in y. When H0 is rejected, this indicates that at least there is one independent variable that is explaining the variation in the values of y. And there is another alternative also, that there can be more than one explanatory variable which are helping in explaining the variation in y. So, now the question is this: we would like to identify those variables which are contributing and those variables which are not contributing. So, in order to do it, we have to proceed one by one. One by one means we have to go stepwise, and we need to test the significance of regression coefficients one by one. So, now we try to discuss here the test of hypothesis for individual regression coefficients. Right. And these regression coefficients are based on our assumption that well, they are responsible for the rejection of null hypothesis. So, since we have considered the regression coefficient beta 2, beta 3, beta k, so now I would like to develop a test of hypothesis for individual beta. Okay. So, let us try to postulate our null hypothesis, say H0 beta j is equal to, say here, 0, right, and j goes from here to k. You may also recall that in the case of simple linear regression modeling, we had discussed the construction of test statistics for testing the significance of slope parameters H0 beta 1 is equal to beta 1 naught. So, this test of hypothesis now in our case, that is going to be based on the similar lines what we did in the case of simple linear regression model. But in this case, our alternative hypothesis in which we are interested is H1 beta j is not equal to 0. So, now in the case of simple linear regression model, we had two cases: when sigma square is known and when sigma square is unknown. In this case, we can see that we have estimated the sigma square by sum of square due to residual divided by the degrees of freedom. So, here we are interested in the case when sigma square is unknown to us, and that is being estimated from the given sample of data. So, under such an assumption, we can construct the test statistic, say Tj, which is beta j hat minus its given value, which is 0, divided by standard error of beta j hat, which I am denoting as a sigma square Cjj, right, where Cjj is the jth diagonal element in the matrix X transpose X whole inverse. Why? If you try to remember, we had obtained that the covariance matrix of beta hat was sigma square X transpose X whole inverse, and this covariance matrix is giving the variances of beta 1 hat, beta 2 hat, beta k hat on the diagonal terms, and their covariance and their covariances on the off diagonal terms. So, in order to find out the standard error of beta j, we are picking up the variance of beta j hat. So, this is being given by sigma square and the jth diagonal element of the matrix X transpose X whole inverse. Now, this statistics is going to follow a T distribution with n minus k minus 1 degrees of freedom under H naught. And yeah, you can also recall that we are estimating sigma square by SS residual divided by degrees of freedom. Right. So, now in this case, once we have obtained the data, we have calculated the statistics Tj, my decision will become reject H naught at alpha level of significance if absolute value of Tj is greater than the critical value T alpha by 2 at n minus k minus 1 degrees of freedom. Right. So, this is actually a sort of marginal test. Marginal test means earlier we had an analysis of variance which is casting the equality of all beta 2, beta 3, beta k together, and now we are coming on the aspect of casting one regression coefficient at a time, right? And so that is why this is called as a marginal test. Why? Because also the beta j depends on all other explanatory variables also. Variables also except xj. Right. So, now using this thing we can now identify that which are the independent variables are explaining the variation in y and which are not. Simultaneously, I would also like to discuss the aspect of confidence interval estimation. So, in this case, if we try to find out the confidence interval for this for beta j, then the 1 minus alpha percent confidence interval for beta j, j goes from 2, 3 up to here k, is given by the expression. And if you recall, in the case of simple linear regression model, we had obtained the confidence interval for the slope parameter beta 1 and intercept term beta 0. So, here also we are going to follow the similar philosophy. So, I can say here that this beta hat j minus beta j upon is the standard error, that is sigma square hat Cjj. This lies between minus T alpha by 2 and minus k minus 1 and T alpha by 2 and minus k minus 1, and this probability is going to be 1 minus alpha. And based on this, I can find out the confidence interval as beta hat j minus T alpha by 2 and minus k minus 1 sigma hat square Cjj and beta j hat plus T alpha by 2 and minus k minus 1 square root of sigma square Cjj. Right. So, this is the 1 minus alpha percent confidence interval for an individual beta j. So, now here you can also see that that how the theory, concepts and algebra that we had learned in the case of simple linear regression modeling is helping us in developing the model for a case when we have more than one independent variables. Okay, now continuing on the aspect of this confidence interval, this is a confidence interval for an individual regression coefficient. Now we can also construct the simultaneous confidence interval on regression coefficients. Right. So, what do we really mean by simultaneous confidence interval on regression coefficient? So, this is actually a set of confidence intervals that are true simultaneously with probability 1 minus alpha, right. Okay. So, they are also called as say this joint confidence interval. So, now in order to construct a joint confidence interval, we can use the result that beta hat minus beta transpose x beta hat minus beta upon k minus 1 MSRS. This follows a F distribution with k minus 1 and n minus k minus 1 degrees of freedom. Right. Okay. So, now I can write down that we would like to find out the value of beta in such a way such that beta hat minus beta transpose x beta hat minus beta over k minus 1 times MSRS is less than or equal to f alpha k minus 1 and n minus k minus 1 degrees of freedom, and the probability of such an event is 1 minus alpha. So, now 1 minus alpha % confidence region for all parameters in beta is the region which is given by this inequality k minus 1 and this describes an elliptically shaped region. You see, when you have only one parameter, then we have a confidence interval. When we have two parameters and we want to find out their simultaneous confidence interval, that can be a region in the two-dimensional. And similarly, when we go for the higher dimensional, this confidence interval will be transformed into a region. Right. So now this confidence interval is essentially the simultaneous confidence interval for all the parameters beta 1, beta 2, beta k. So this is going to be a sort of elliptically shaped region. Well, after this we come to another aspect, and we talked about coefficient of determination, and this is actually denoted by r square. So now the first question is, what is this coefficient of determination? Now you see, now we have reached to a stage where, using the data on independent and dependent variables, we have obtained a model by estimating the parameters beta 1, beta 2, beta k and sigma square. Now, this estimation technique can be anything, either least square estimation or maximum likelihood estimation. And based on that, we have obtained the fitted model. Now, a basic question is that, how do we know that the model which we have got is good or bad? Or how to judge the goodness of fit of this model? Right. So, this coefficient of determination helps us in determining the goodness of fit of a model. Okay, so first question comes, how should I judge it? In case if you try to recall, in the case of simple linear regression model, what we had done, we had one independent variable x and we had one dependent variable y. We had obtained the data and then we have created a scatter diagram, and it was something like this. So suppose if I try to take here two situations, something like this, x and y, and in which the scales of x and y are the same here, and we try to fit here a line like this and here this. Now, what you can say that which of the model is going to be fitted better. So, obviously, in this figure I can see that the points are lying more closely to the fitted line in comparison to this figure. Right, here you can see that the points are lying here and here. So, and they are quite far away than the points in figure number 1. So, this gives us an idea that in case if the points are lying close to the line, that means our model is better fitted. One simple option to measure this quantity is to find out the correlation coefficient between x and y. So, obviously, in case of figure number 1, the correlation coefficient will have a higher value than in figure number 2. This concept is extended, and this is used to judge the goodness of fit in a multiple linear regression model. Now, we try to extend the concept of simple correlation coefficient, and we try to use the concept of multiple correlation coefficient. So, in case if I define say R be the multiple correlation coefficient say between y and x1, x2, here say xk. Then the square of this multiple correlation, which is connoted as R square, this is called as coefficient of determination. And the utility of R square is this, that it describes how well the sample line fits to the observed data. And in some sense, this measures the goodness of fit of the model. And it also measures the explanatory power of model, and this reflects the model adequacy in the sense that how much is the explanatory power of the explanatory variables. Right. So, in simple sense, I would say now R square is a measure that will give us an idea that the model which we have obtained, whether this model is good or bad, and if good, how much this is good, and if bad, how much this is bad. Okay. So, we try to consider here the model, and we consider here a model yi is equal to beta 1, beta 2 xi2 plus up to here beta k xik plus epsilon I goes from here 1 to n. One very important thing we have to keep in mind, that we are assuming here that intercept term is present. This R square has a limitation that it assumes that the intercept term is present in the model, and the value of R square can be obtained only in such a condition. If you do not consider the intercept term in the model, then the definition of R square which we are going to consider here, this will not remain valid. Okay. So, now in this case we try to define the R square as 1 minus say sum of square due to residual divided by sum of square due to total. Right. Now, if you see the interpretation of this R square, under what condition you would call that a model is good fitted? The model is good fitted when the contribution of the random error component in the model is as small as possible, and say ideally this should be equal to 0. So, now this can be written as SST minus SSRes divided by SST. Now, you may recall that in the case of analysis of variance, we had proved that SST is equal to SSReg plus SSRes. Okay. So, now if I try to use this relation over here, this can be written as SSReg over SST. So, now the expression for this R square will simply be now here 1 minus SSRes, that is epsilon hat transpose epsilon hat divided by summation I goes from 1 to here n yi minus y bar whole square. Now, the question comes, how do we ensure that this definition of R square is giving us what we want? Right. If you see in a good model, what will happen? For example, if I try to consider this expression R square is equal to 1 minus SSRes over SST. So, model will be good in case if the contribution due to random error is as small as possible. And in that case, ideally we would assume that sum of square due to residual should be 0. So, in this case, if I say that if sum of square due to residual is 0, then R square equal to 1, and this is in best fitted model. And that would be an ideal condition in which we are all interested. Now, on the other hand, in case if the model is not at all good fitted, that means the contribution of the sum of square due to regression is 0. That means none of the x1, x2, xk variables are helping us in explaining the variation in the values of y. And in that case, when the sum of square due to regression becomes 0, then SST is equal to SSRes, and R square in this case becomes 1 minus 1 over 1, that is equal to 0. So, this would be indicating the poorest fit of the model, or rather I would say that this is the worst fitted model. So, now we see that the value of R square is lying between 0 and 1, and R square is equal to 0. This indicates the poorest fit, worst fit, and R square equal to 1, this indicates the best fit. Now, if I try to take any other value of R square, say for example 0.95, then this indicates that 95% of the variation in y is being explained by the fitted model, or the independent variable x1, x2, xk. This R square has one limitation, that value of R square increases as number of explanatory variables increases. Now, why this is a limitation? Now, suppose somebody is trying to fit a model with a certain number of explanatory variables. Now, some more variables are added in the model which are not relevant. They are simply useless variable. They are not affecting at all the values of y. So, this does not indicate that the model will get better by using those irrelevant variables. But when we try to do so, the value of r square will increase, and that would indicate my model is getting better and better. So, in order to handle this limitation, we can define a variant of r square which is called as adjusted r square. Right. So, this adjusted r square corrects this limitation. So, now we discuss about the adjusted r square. This adjusted r square, this is denoted by r bar square, and this is defined as 1 minus sum of square due to residuals divided by n minus k upon sum of squares due to total and divided by n minus 1. So, this can be further simplified as 1 minus n minus 1 over n minus k times 1 minus r square. Okay. Now, if you try to observe what are we going to do here, we are trying to divide sum of square due to residual by n minus k. So, if you try to recall what was your n minus k in the context of sum of square due to residual, this was actually the degrees of freedom associated with the distribution of SSRS in the context of analysis of variance. And similarly, if you see, we are trying to divide the total sum of square SST by here n minus 1. So, here again this n minus 1 is simply the degrees of freedom associated with the distribution of SST in the context of analysis of variance. Right. So, this adjusted r square helps us, and it does not increase as the number of independent variables are added in the model. But on the other side, adjusted r square also has certain limitations, right. So, first the limitation is this, that adjusted r square can be negative. Right, this is difficult to believe that well, that is a square quantity, but if you try to see this is a function of n, k and this here r square. Yeah, r square cannot be negative. For example, if I try to illustrate this limitation, let me take a hypothetical example that k is equal to 3, n is equal to 10 and r is equal to 0.16, and then r bar square will be 1 minus 9 over 7 into 0.84, and this value turns out to be less than 0. So, obviously, now you can see here that r bar square has no interpretation. On the other hand, if we try to look at this situation from the application point of view, I would argue that in practice such situations are very rare to occur. Why? Because if you see, we are here getting a value of r square which is 0.16. That means the fitted model is explaining only 16% of variability using the variable x1, x2, xk. So, obviously, this is already indicating that the linearity of the model is questionable. So, in this situation, even I would not like to use the multiple linear regression model, but rather I would try to fit some other model, right. So, now after this, let me try to explain that what are the limitations of R square. Well, R square is a very popular goodness of fit statistics among all the user in experimental sciences, but it has got some serious limitations also. Right. First limitation we already have discussed, that if constant term or the intercept term in the model is absent, then R square is not defined. Yeah, this can also be shown mathematically, but I am skipping the proof here. And in case if someone is considering a model without the intercept term, and still if he or she tries to find out the value of R square, there is a risk that the R square value may turn out to be negative. Okay. The next question comes, then if someone is trying to fit a model without intercept term, then how the goodness of fit of a model can be judged? Well, there is no unique answer. In the literature, some ad hoc measures have been defined, but definitely there is no guarantee that those ad hoc measures will give us a good statistical outcome. But anyway, this is the limitation of the R square, and this is how it has to be used. Okay. The second limitation of R square is this, that R square is sensitive to extreme values. So I can say in simple word that R square lacks robustness. Now, coming on the quick issue from the application point of view, that we know that when we are going to fit a model to a given set of data, we need to first make sure that there are no extreme values in the given set of data. And in case if they are present, there are some other ways to handle them. So ideally, this condition will not happen in practice if somebody is carefully making a model. But definitely in case if somebody is ignoring this aspect, then R square will lack the robustness. And the earlier we had also discussed the third limitation, that R square increases as the number of explanatory variables increases. Right. Now let me come to a different type of situation where we are interested in comparing two different models. Suppose there is a situation and there are two models which are fitted. Suppose the model number 1 is, say, yi is equal to beta 1 plus beta 2 xi2 plus, see here, beta k xik plus epsilon I. And second model is that the model is fitted using the same data, but by taking the log transformation, that all the values on the response variable, their log is taken, and then the model is fitted. Right. So in this case, yeah, I would like to denote the regression coefficients by, say, gamma 1, gamma 2, gamma k in place of beta 1, beta 2, beta k. So the model can be written as, say, here xi2 plus here gamma k xik plus suppose some random error component epsilon I. Right. In this case, if we try to define the R square, then for model number 1, the R square is, suppose R1 square, that is defined as 1 minus summation I goes from 1 to n yi minus yi hat whole square divided by I goes from 1 to n, say yi minus y bar whole square. And now we have to define the R square for model number 2. Now there can be various possibilities. For example, one simple option I am not saying that this is the only option. There can be many other options. One option is that 1 minus summation I goes from 1 to n, say log of yi minus log of yi hat square divided by I goes from 1 to n log of yi minus log of y bar. Here also someone may argue that instead of taking log of y bar, he would like to consider the arithmetic mean of log of yi's, that first he take the transformation and then finding out the sample mean. But anyway, that is not my objective here to discuss those things. But it is clear from the values of R1 square and R2 square that these two values are not comparable. So now the issue is very simple, that two different persons or the same persons have obtained two different models, and he wants to know out of this model number 1 and 2 which is a better fitted model. So this cannot be obtained using the definition of R square. So I am not saying at all that R square is a bad measure, but R square is a very good measure. R square measures the goodness of it, but it has some limitation and it has some nice properties. So I would suggest that use R square, but be careful, handle with care. Okay. This R square has also got a relationship with F-statistics that we had obtained in the case of analysis of variance. You see how? If you recall that in the case of analysis of variance, we had considered the model yi is equal to beta 1, beta 2 xi2 plus here beta k xik plus epsilon I. And at that time also I had told that we are going to consider here the presence of interceptum in the model, because that we will use later on to establish a relationship between R square and this F statistic. So now this is the situation we are going to use it here. So if you remember that our null hypothesis in the case of analysis of variance was H naught beta 2 equal to beta 3 equal to beta k is equal to 0, right. This was your under analysis of variance, right. Okay. And based on that we had finally obtained the F statistics, which was obtained as mean square due to regression divided by mean square due to residuals, and this was actually n minus k upon k minus 1, SS due to regression and SS due to residuals. Now this can further be expressed as say n minus k over k minus 1 and SS regression, and now using the relationship that total sum of squares is equal to sum of square due to regression plus sum of square due to residuals, I can rewrite sum of square due to residual as total sum of squares minus sum of square due to regression. So this can be written as say here n minus k over k minus 1 SS reg divided by SST divided by 1 minus SS reg divided by SST. So this comes out to be nothing but n minus k over k minus 1 and then r square over 1 minus r square. So you can see here that there is a closed form relationship between the F statistics of analysis of variance and R square, and both are very closely related, and then they have a very close interpretation also. So F and R square are closely related. You see how? When I say suppose R square is equal to 0, then in this case F also becomes 0, and when we say that R square is equal to 1, then F becomes infinity in limit, right. So this implies that larger the value of R square, this implies greater the value of f. Right. So, now what is the interpretation of this thing? So, I can conclude that if f is highly significant, that means the test of hypothesis based on this F-statistic is indicating that that all the regression coefficients are significant, then we can reject H naught. And when we reject the hypothesis H naught, when all the variables x2, x3 up to xk, they are relevant variable and they are helping in explaining the variation in y. So, I can conclude that y is linearly related to x2, x3, xk, and that is what we had also said in case of analysis of variance, that this is a test of overall adequacy. So, now one can see that there is a close connection between F-statistics of analysis of variance and this R square, and their interpretations are also related. So, when we are going for the software issues, then we will see that the software outcome consists of R square values, adjusted R square values, as well as the analysis of variance table. So, looking at the outcome of software, we try to make different types of conclusions for the fitted linear regression model. So, now we stop here in the topics of multiple linear regression model, and in the next lecture we will come up with some other issues. Till then, goodbye.